Raise your hand if you can remember where you were at this time exactly 1 year ago. We've got a few people in the audience that raised their hands, but unsurprisingly, the majority of you haven't. To those of you that didn't raise your hands, while you didn't know where you were, your phone does. Every moment that your phone is in your pocket, which in the modern world is effectively always, it has recorded your location down to an accuracy of plus or minus 10 meters. This power was made possible with the measurement and the memory capabilities of computers. Now, humans and computers have fundamentally different views in the world. We humans see the world as a continuous flow of sounds, colors, tastes, smells, and feelings. We do not attach numbers to the way we perceive the world around us. Computers, on the other hand, see the world in distinct, quantized units. They have no ability to understand continuous values, and thus are inherently limited. Values that appear to us continuous, such as time, must be numerically approximated in order to be computed. This numerical approximation of continuous values, the digitization of analog values, is a powerful tool that forms the basis of measurement. My Keystone harnessed the memory and the measurement powers of computers to record the main indicators of climate and weather. Parameters such as rainfall, air pressure, temperature, shortwave radiation, wind speed, and wind direction are translated into a set of quantified values through the use of computers and analog to digital converters. The result of this investigation can be seen here in the form of a weather station. Now, I've included this image to show you the spatial orientation of the sensors and get you an idea of the scale of my weather station, but originally this diagram was made to aid in the construction. Down on the left, we have the barometric pressure sensor, and at 2 is the rain gauge, at 3 is the temperature sensor, at 4 is the wind speed and direction sensor, at 5 is the shortwave radiation sensor. All these sensors are posted at standard heights according to the World Meteorological Organization and Environment Canada. The entire station is 12 meters tall, or for any of the Americans in the room, 40 feet, and was welded together by my advisor on this project, Court Ashbaugh. The station itself is 7 kilometers as the Whiskey Jack and the Bald Eagle flies straight to the northeast of our current location here in the MPR. But as the Tyler goes, it is 15 kilometers on a dirt road and then another 7 kilometers of a hike until I finally get to the subalpine location at 1,450 meters. So this is the only weather station within Garibaldi Park and is the only permanent weather station infrastructure ever to be present within Garibaldi Park. The 55,000 annual users of the park will greatly benefit from this data set, and if you're familiar with the area, you know that the span from Squamish to Pemberton is not a short distance. This area, which now has a reliable data set for climatology and meteorology, will further these scientific fields. You might be wondering how I got this 12-meter pole from Quest University all the way up to the weather station site. The answer is not that it was taken up with a cornerstone class as an initiation ceremony. Although this was pursued for about 2 weeks. Not actually kidding. The answer is that it was brought up with a helicopter. Through the downwash and the communication errors that happen when wind is blowing down on you and all you can do is do hand signals that you haven't previously coordinated, we somehow were able to situate this vertically. Now, the station didn't come out of nowhere. It had humble beginnings, first starting in the class that I took here at Quest University, Experiments in the Physical Sciences, with my advisor, Court Ashbaugh. It was a single computer and a single temperature sensor that I moved from the freezer to the fridge, to the lab, and eventually on an exciting day, actually outside so I could record real weather. The bulk of my investigation, however, happened when I secured a fellowship here at Quest University for the summer of 2014. I moved the station up to the roof of the academic building, the round building that you passed on the way here to the MPR, and added more sensors, incorporating them into the system. Now, this was my favorite part of the process because it involved taking these different sensors that aren't supposed to work together and incorporating them into a system that allows us to understand climate and weather. Although the physical stature and maybe even the scenery of this site is more impressive than taking this data logger box from here to the situation over here, that's where I spent 95% of my time. That's where all the real effort went in. And now, within that 95% of my time, probably 60% of that time went into the GSM shield, or the little module that allowed me to connect to the internet real time. After 4 months of troubleshooting and adding external watchdogs and antennas, I'm happy to say that I haven't missed a single 15-minute data interval for the last 2 months. The user-friendly website, which went live this morning, can be seen in the upper left, or the upper right, still haven't learned my left and rights, the upper right of the screen. Down at the bottom is the raw data website that's been live for the last 2 months. Now, a skier in Vancouver might do a superficial analysis of these data and might see that it is 6 o'clock in the morning, the wind is calm at about 3 kilometers an hour, that it's a warm morning at 4 degrees, and he's actually just catching a sunrise. As you can see, you probably can't see from the back, but the values go from 0 to some positive value, indicating that it goes from no sun to sunrise. Beyond the superficial analysis, we can do a more in-depth analysis to understand hazards of the park. Now, this is a popular backcountry skiing location, and although most of the slopes are actually below the threshold of 25 degrees, which is necessary to have a large avalanche, there are some isolated slopes that do pose an avalanche hazard. One of the main contributing factors to avalanche safety is wind loading. Wind loading can result in the formation of wind slabs and cornices, which pose avalanche hazards. Locations of these structures, or situations in the case of a wind slab, can be predicted by understanding 2 variables that my weather station records: wind speed and wind direction. Because wind is a vector, or a quantity that has both a magnitude and a direction, we can represent it as such. Here in this diagram, 1,000 data points, or 10 days worth of data, is represented with each 15-minute interval as a single wind vector. As you get farther away from the origin, this signifies a higher wind speed, and the orientation on this graph, according to the origin, signifies the orientation in terms of cardinal directions. You can see north and south for the y-axis, and east and west would be for the x-axis. Just from looking at these data, you can understand that most of the snow would be moved to the west, and more specifically to the west-northwest. But to get a more easily understandable way to understand these data, we can divide this into 30-degree sectors and then represent it on this radar graph. Now it becomes obvious that most of the snow is going to be blowing to the west, northwest, and west, and therefore slopes that are facing this direction will see the highest avalanche hazard. Taking this out to the actual site, you can see Round Mountain, the most prominent feature in the local area, at the top of this image, and a weather station down at the bottom. Here's the wind vector that we were talking about earlier. Here's that same wind vector on the top of these slopes, so you can imagine where the cornice growth and the wind loading would occur. Here are the avalanches that would occur from the failure of a cornice or the slide of a wind slab. And here is the summer path that goes directly below. Now, BC Parks is aware of this hazard, so they reroute the path around the south side of Round Mountain during the summer. This is an example of how hard data can be used to predict hazards from the park, and is just an example of one of the many applications of these hard data. So I had 4 main goals when I started this project. I wanted to have station reliability, installation at the final site, real-time data access, and I wanted to have a user-friendly website. Although it came down to the wire, I'm happy to say that I've achieved all of these goals. But that isn't to say that I don't want to see more improvements in the future. And just because I'm graduating here at Quest doesn't mean that the weather station is going to stop existing and improving. So I'd like to see the addition of a webcam, a snow-depth sensor, and a humidity sensor. But more importantly, I'd like to see a forecast verification study performed. This would be a comparison analysis of the 3 Environment Canada models, the regional, the global, and the high-resolution model, to my observed data at the site. It would give Environment Canada an idea of the biases and the accuracies of these forecasts, and give recreationists an idea of the limitations of these forecasts, and then understand which situations these forecasts are more appropriate for. The final piece, and I think the most exciting to myself, would be to incorporate my data into the Environment Canada network. This would be a real-time incorporation into their forecasts, would improve local forecast accuracy, and would result in obvious benefits to the local community. So I experienced a variety of weather throughout the installation of the weather station, but as many of the skiers in the room can attest, this winter had an overarching theme. To skiers, it was crappy, but maybe in a more objective sense, it was warm. Here are the observed values from the end of February and early March, and here are the expected highs and lows for this region, elevation, and time of year. Obviously, these are unusual, but they allowed me to complete the installation of the site. So, another reason that I put lucky in quotes is that although I cannot directly attribute this warm winter weather event to climate change, what I can say is this. 2014 was the warmest year since recording started in 1880. According to the Intergovernmental Panel on Climate Change, warm winter weather events like this will become more common in the years to come. While measurement and empiricism were what allowed humans to extract resources with such efficiency that we could affect large-scale Earth processes like climate, it can also help increase awareness of our effects. My weather station, through the power of measurement, is a good example of this. The Garibaldi Park weather station has data that are valuable at this moment right now. But in the future, with the changing climate, these data will only become more valuable. Thank you.
Oh, excellent. Very good.
Great, we'll take questions for our speaker. Yes?
Are you in the line of the avalanche weather station, or are you both that weather station language is not found?
No, the weather station is actually located in the flattest spot that I could find in this area. There were a lot of considerations that went into the location, but having it on a ridge, you're actually kind of recording a microclimate, so you want to have it in the meadow so it can be easily compared with other data. So it's in a safe location, is the short answer. Yeah.
Yes?
So, based on your data and the data of the closest sites to yours, how anomalous do you think the winter has been?
It's hard to say. You know, I wanted to do a comparison analysis of just the Squamish data to my weather station, but I didn't have time. Like I said, a lot of things came down to the wire, and I'd love to pursue some similar study to this, continue another year at Quest, but like the other people have been saying, it's time to move on.
Were there any hurdles in installing a 40-foot tall metal pole in the provincial park? And if so, what does this look like?
That's a good question. The one main hurdle was actually getting the approval of the Squamish First Nations, because they have jurisdiction on who can install infrastructure in areas like this. I had to send them a series of proposals, and then after the third proposal, nothing was really going through, but what actually made the weather station be able to be installed was having someone that previously had a relationship with the First Nations, talk to them, tell them about the situation, and once they realized that it was an academic pursuit and it wasn't for any sort of monetary benefit, they were enthusiastic about the idea and went through. But it was about a 3-month process to get that approval.
Yes, Chris.
How are you calibrating the weather station to know that the data is accurate?
It's a good question. Now, I calibrated all of these instruments in a lab setting, but it's important to understand that when you move these instruments, because they're a little bit finicky, it can actually change their accuracy. So I compared them to the portable weather station that we have here at Quest. So I brought it up to the site, and then the portable weather station, which was recording wind speed at a 3-meter height, and my weather station, shown here as the permanent weather station, is recording wind speed at a 10-meter height. So you'd expect my wind speed to be higher and the 3-meter wind speed to be lower. Here is wind direction. Here you can see our in good agreement my shortwave radiation values and the portable weather station shortwave radiation values, and here are temperature values. So this is just an example of how I know that the data I'm recording is accurate.